Gauss's law is an expression of the relationship between net electric flux through a closed surface and the charge enclosed by that surface. The closed surface is often called a Gaussian surface. In Gauss's law, the net flux through any closed surface surrounding a point charge q will be given by q over epsilon naught, and it is independent of the shape of the surface. We'll explore this in 3 examples below. But first, it's worth mentioning that epsilon naught is the permittivity constant of free space. It tells us how well the electric field permeates through space. And it has a value of 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. We'll find that the net electric flux through a closed surface that surrounds no charge will be 0. But Gauss's law will be valid for the electric field of any system of charges or any continuous distribution of charge. And although Gauss's law can be used to find the electric field E for any charge configuration, we'll find that in practice it's really limited to symmetric situations. Keep in mind that the Gaussian surface you use to calculate the flux can be chosen by the problem solver, and it doesn't have to necessarily coincide with a real surface of any kind. We want to try to choose a surface that satisfies one of these conditions. It's advantageous if the electric field's magnitude can be argued to be constant over the entire Gaussian surface. It can be helpful if E and A are parallel or if E and A are perpendicular. Sometimes we'll argue that the field can be 0 through the whole Gaussian surface. Let's look at some examples though. Here we want to find the total electric flux through a Gaussian sphere of radius 1 meter. And I'll assume that the particle enclosed by this surface is a proton. An analysis of the situation could start with a drawing of the electric field that a proton emits. So, as we know, positive charges will generate a field that points directly away from themselves. And as we can see, the magnitude of the field would be constant at all these different points around the proton at that radius of the sphere. So these are the electric field vectors. Notice that the electric field vectors form a 90-degree angle with the area of the surface. And this is really helpful to finding the net flux. So here we see that at all points, on the sphere's surface, E and delta A are perpendicular. Not only that, but the magnitude of the electric field is also constant at all those points. So in this particular case, the electric flux will simply be given by the magnitude of E times the area of the sphere. But this means we have to find both of these things. We have a rule for electric field. It's K Q over R squared. And we have a rule for area of a sphere. It's going to be 4 pi R squared. That's just from geometry. So we'll plug in everything we have. I get 1.81 times 10 to the minus 8 Newton meters squared per coulomb for the electric flux. Now, so far, I didn't use Gauss's law. All I did was I used our concept of electric flux being the product of a field and an area. But let's find the electric flux through the larger sphere. As we've seen, the electric field at these points should be weaker than the electric field was for the smaller sphere. Because we've got a much larger radius, and basically the field that the proton emits has to be spread out over a larger surface. Let's repeat the calculation using a radius of 2 meters this time instead of 1. We can see an interesting thing in the mathematics here. What we see is that no matter what the radius is, it's going to cancel out. And interestingly, we get the same flux here as we did in the previous sphere. So this tells us something fundamental about the way that charges propagate electric field through space. When you decrease the field and increase the area, the amount of flux still remains the same. And that's critical to Gauss's law. According to Gauss's law, the electric flux will always be equal to the charge enclosed over epsilon naught for any given surface. Gauss's law is one of 4 fundamental equations which explain all of electromagnetism. Let's try calculating the electric flux this way. Our charge enclosed is 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton. And for epsilon naught, we have this. Gauss's law tells us the net flux through that surface is 1.81 times 10 to the minus 8 Newton meters squared per coulomb. Now, why would we want to use Gauss's law? Well, if I wanted to know the net flux through this cube, it would be quite difficult in practice to calculate it based on field and area. What we would find is that the field would be stronger at points which are close to the proton, and it would be weaker at points that are farther from it. So the field strength on this cube would not be constant. So here, Gauss's law could be useful to find that net flux. I don't even have to use the geometry of the cube to know that the net electric flux through that cube is going to be 1.81 times 10 to the minus 8. Before I end this video, I'll mention that Coulomb's constant is also defined as 1 over 4 pi epsilon naught. Epsilon naught is 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared. And we know that K is equal to 8.99 times 10 to the 9 Newton meters squared per coulomb squared. You can verify that this is true by just plugging in your 8.85 into the formula, and you'll see that it is valid. So if we are to start with Coulomb's law for fields, E equals K times Q over R squared, we could plug in for K. And get another form of this important law. For any sphere, 4 pi r squared would be the area of it. So we would get this, and then if we multiply that area to the other side, we get this result, which is a formula that we often use for finding the flux through a surface. This reveals the formula for Gauss's law.